Hello everyone, today I will introduce our paper presented at the HKE International Conference on Mobile Data Management. The paper is titled Collaborative Preparedness of Emergency Incidents in Unmanned Storage Warehouse. I will take you to understand our research from the following four parts. Part 1. Introduction. With the repeated development of model logistics in order to remove the influences of warehouse system, people's research on warehousing gradually turns to be intelligent and unmanned. However, in the operation and management of warehousing system, emergent incidents cannot be completely avoided. For example, the offset position of goods may occur in Finger 1. Malfunction of automatic guided vehicles may occur in Finger 2, and collapse of storage racks may occur in Finger 3. This instance will interrupt the original unmanned warehousing task process. Traditional manual maintenance requires technicians to repair on-site, which makes it difficult to timely control emergent incidents. There are several challenges. At first, detection response programs may extend the time of the task completion, missing the optimal window of time for troubleshooting. After that, the emergency may escalate into an irreversible disaster. Secondly, unmanned warehousing is a complex environment which usually has a large area, a large number of goods and equipment. Thirdly, the trade-off between maximizing the complete rate of the original tasks and minimizing the damage caused by emergent incidents should be considered during optimization. Therefore, we have the following contributions. Propose an emergency preparedness method based on BI-LSTM and DQN in order to maximizing the completion of original tasks, as well as minimize the damage caused by the incidents. A simulation environment is established based on a realistic environment, and the experimental results show the superiority of the performance of the proposed method. Part 2. Problem descriptions. We constructed two graphs. The first is undirected graph G based on the paths and the regions in unmanned warehouse, and the second is graph G prime based on the diffusible paths of emergencies occurring in G. In graph G, the uppercase letter V represents the node set of different task areas and shelves in the unmanned warehouse. Each node contains the attribute W, which means the goods value. The uppercase letter E is a set of edges connected between nodes, and the attribute D on the edge represents the distance between connected nodes. The uppercase letter O is a set of initial delivery tasks. In each delivery task, V represents the local of the delivery task shelf, ET represents the deadline of the task, and W represents the value of the delivery goods. In graph G prime, the uppercase letter V prime corresponds to V in graph G. The both sets has the same size. Each node V prime has an attribute Ft to indicate the incident state or severity of node. The set E prime represents the adjacent nodes that may be affected in the next time step, and the attribute G Ft on the edge E prime Ig represents the possibility of diffusion to node V prime G when node V prime I has an incident. Given G, G prime, and O, we predict the nodes when new incidents are likely to occur in the next few time steps. Then, on the condition of ensuring the maximum completion of all delivery tasks, a kind of emergency preparedness is obtained. That is, the maximization value of the final initial delivery tasks is expressed as the following formula, where W represents the sum of the value of all tasks completed at time t. Part 3. Proposed solution. Our method is divided into two parts. First, while LSTM is used to predict the nodes that will have an emergency. Second, DQN algorithm generates the emergency present schedule for the nodes. We will use three features of all nodes to calculate the probability of incidents occurring in the next time step by LSTM. The first feature is FT, which reflects the state of emergency of shelf nodes and affects the diffusion probability of emergency. The second feature, FW, reflects the property of goods on shelves and indicates the degree of vulnerability to the diffusion of emergency. The third feature reflects the correlation of emergency diffusion between adjacent nodes. We construct a n multiplies 3 matrix as the input of by LSTM, where n is the number of shelf nodes. Each line consists of these three features above. The output is mapped to a n multiply 1 dimensional vector and a convolutional neural network with a convolutional kernel of 1 multiplies 3 represent the probability G of incidents occurring at the next time step. The G bigger than 0 will be regarded as a potential dangerous nodes and added to the set of emergency prediction VP T plus 1. The rescue agents are dispatched to the nodes in the set VP T plus 1 for emergency preparedness. Given VPT plus 1 and the current location set LT of the agents, DQN algorithm can be used to schedule. There are three main states obtained at time t. First, a global state, which refers to various workplaces, distribution of goods on shelves, and all feasible paths. Secondly, the state of agents includes their locations, current tasks, available tasks, and follow-up task sequence. Third, the current state of instance includes the scope of impact, the number of schedule agents required. The action set A is composed of the dispatch of a rescue agent. After the agent arrives at the target location, it can get the reward R according to the instance state of the target location. Part 4. Experimental results and discussion. The specific setting of the experiment scenarios are as follows. Experimental evaluation index are reward R, delivery task completion rate S, and emergency damage rate F. The formulas are shown on the right. Taking the number of rescue agents as 4 and the number of emergencies as 8, the degree algorithm, DQN algorithm, and PDQN algorithm were adopted. After 10,000 rounds of training, the experimental results are shown in the following figures. It can be seen from figure A that among all the algorithms, the proposed algorithm PDQN has the highest completion rate of initial delivery tasks, reaching 19%. The initial delivery task completion rate of graded algorithm is too oscillating, basically keeping at about 60%. Figure B shows that the damage rate of PDQN begins to converge at 1,000 times. After convergence, the damage rate of the emergencies can be as low as 11%. Which is the lowest among these three algorithms. As can be seen from figure C, compared with DQN, the reward function of PDQN converges faster and improves more after the prediction mechanism is added. That's all. Thank you very much.